See, this structure looks scary and devoid of any possibility of life, but this is our home, the Earth. At the beginning of its existence, 4.6 billion years ago, its formation and the formation of the Moon remains a mystery. Today, we'll tell you about the theories that scientists have suggested. You'll learn how planets so different from each other form from the same material, what planet crashed into the Earth in the past, how much water there is on our planet and where it came from, and finally we'll tell you how old the oldest organism on Earth is. We prepared the story of our planet from a clump of dust and gas a few miles in diameter to the appearance of life. When the Sun was created, gases and other materials around it started colliding with each other and forming small bodies called planetesimals. As the gravitational forces were growing, more material was pulled together, and these seeds of planets grew larger until they became true planets. The solar system's gas giants, Jupiter and Saturn, Uranus and Neptune, were born much earlier than the four known terrestrial planets, Mercury, Venus, Earth and Mars. But how exactly was our home planet born? The Earth's story started about 4.6 billion years ago in a disc-shaped cloud of dust and gas rotating around the early Sun. We know it was that long ago because of the fossil record, one of the most simple methods to determine the age of our planet. Scientists were able to find zircon crystals that are roughly 4.3 billion years old. So far, these crystals are the oldest materials found on our planet. But how exactly our planet was formed remains a scientific mystery. However, there are two leading theories on planetary formation. The core accretion model is the first one and the most widely accepted. About 4.6 billion years ago, there was a solar nebula consisting of spinning gas and dust particles from which our Sun was born. Then, as the remaining material of different sizes orbited our star at slightly different speeds, it started to collide and stick together under the effect of gravity. Smaller particles grew into larger particles that ranged from miles to hundreds of miles in diameter. The solar wind would then sweep away lighter elements such as hydrogen and helium, so that just rocky materials would stay closer and turn into terrestrial worlds. The process continued until these space objects reached thousands of miles in diameter. But far away from the star, the Sun's constant stream of charged particles doesn't have a very strong impact on lighter elements. As a result, these elements combine and transform into gas giants. What's exciting is that NASA believes this is the way planetary formation works. Small rocky worlds like Earth are a lot more common throughout the universe than gas giants. The thing with this theory is that it works well to explain the formation of terrestrial planets, but has problems explaining the creation of giant worlds. This is because scientists believe the gas disk around our Sun only lasted about 4 to 5 million years, and simulations based on the core accretion model show such planets form longer than that. However, the second theory, or the disk instability model, resolves this issue. This newer idea suggests that chunks of dust and gas clump together early in the existence of the solar system, and over time, these chunks slowly turn into a gas planet. But the difference is that this way, planets can form much faster than those explained by the core accretion model. In fact, according to this theory, it could happen within as little as 1,000 years. A planetary formation this fast makes it possible for such worlds to trap the rapidly vanishing lighter gases. A recent study suggests that proto-Earth was formed within about 5 million years. And on a cosmic scale, it's nothing. If we converted the solar system's estimated 4.6 billion years of existence into a 24-hour period, these 5 million years would be equal to just about 1.5 minutes. If scientists are right about this, water could be just a byproduct of the formation of a planet similar to our home. This would mean that we're a lot more likely to discover the ingredients of our life outside our solar system. And what about our satellite? What's the story of the Moon? Astronomers have proposed many hypotheses for the origin of our satellite, and some of them are quite bizarre. The fishing theory suggests that the moon was once part of our planet. When the Earth was still a hot ball of spinning lava, it may have ejected the material our satellite is made of. Now, while most scientists remain skeptical because of how fast our planet must have been spinning to make this happen, it would have been a breathtaking phenomenon to observe. The capture theory is yet another interesting idea, suggesting that the moon could have been captured from a different part of the solar system. We already know that some worlds have gained their moons in such a way. Perhaps before it was attracted by our planet's gravitational pull, the moon was orbiting Venus. Still, this wouldn't answer the question of why the Earth and the moon have almost identical oxygen and isotope ratios. But the next theory could. Some astronomers think our satellite was created side by side with the Earth. The idea is that both were formed at about the same time from the same gas and dust and at the same part of our solar system's protoplanetary disk. The theory is called co-formation, and it fits because of the isotopic similarities between the two space objects. But at the same time, it cannot explain the difference in the size of their iron cores. The leading and perhaps the most mind-blowing theory is that the moon was born as a result of a giant impact with a different celestial body. There's a chance that Earth wasn't the only planet that was forming 150 million kilometers from the Sun. Earth's creation may have been accompanied by another planet dubbed Theia. This strange world must have been smaller than our planet, just about the size and mass of Mars. At first it could have had a stable orbit, but as Earth increased its mass by gathering more material, Theia's orbit was destabilized, and so it swung back and forth towards our planet until eventually the two protoplanets collided. The speed of the collision was low, so the Earth wasn't destroyed. However, the impact must have created a disk of debris, molten rock and hot gas that became the building blocks of the moon. Both Theia and the Earth could have been composed of a combination of materials, and more of the lower density splatter would eventually transform into the moon. If this is the case, it explains why our planet has a higher density and thicker core than our satellite, and why the Earth and the moon spin the way they do around each other. But let's get back to Earth. Throughout the next 500 million years, the Earth resembled a ball of molten surface. Volcanism, asteroid impacts, and several other factors made it extremely hot. Gravitational compression, radioactive decay, and asteroid impacts. A big amount of this initial heat is still there, deep inside our planet. But as it cooled, minerals started to crystallize, and because of the different densities of materials, the crust, mantle, and core were formed. So how did water appear on a hot rock floating through space? Oceans cover more than 70% of the Earth's surface. This is 1.386 billion cubic kilometers of surface water or ice. But the fact that there is more liquid water on our planet than any other known rocky world in our solar system isn't fully understood. As with the Earth and Moon, there are several hypotheses as to how water appeared here. One likely reason is extraplanetary sources, such as comets, trans-Neptunian objects, or even protoplanets. There is actually a lot of water in our solar system. 2/3 of Uranus and Neptune, for example, are made of ice. So, if our planet was born hot and dry, then water must have come from somewhere else, brought by icy comets and asteroids. Comets are made of dust and ice, with most of that ice being frozen water, so they might be the clue. But measurements show that comet water has a lot more deuterium in it compared to that found on Earth. What about asteroids? Because their ratio of deuterium to normal hydrogen water is closer to that which we have on our planet, they are an even better candidate. Also, asteroids are 20% water, but due to their small size, there must have been a colossal number of impacts to explain all the water on our planet. To fill the planet with 1,386,000 cubic kilometers of water might seem like a lot. To compare, this much water would have been enough to cover the contiguous United States to a depth of roughly 145 kilometers. But this still isn't a lot. In fact, water amounts to only about 0.02% of our planet's mass. Since Earth experienced periods of heavy bombardment in the past, this is actually a possible scenario. Researchers also think that when our planet formed, huge amounts of hydrogen were captured in its rocks and minerals. Because of the mantle's heat, hydrogen and oxygen-rich minerals started to melt, which made it possible for water to spew out from the Earth's crust. According to scientists' estimates, about 10 oceans of water could exist within the mantle. Probably the most astonishing of all is the volcanic outgassing hypothesis. According to this idea, water may have come from volcanism. In other words, it was always there in the form of minerals, with oxygen and hydrogen hidden beneath the crust of our planet. Volcanoes only helped it break free as vapor. It originated in volcanic eruptions, then condensed and fell as rain. Scientists think that all volcanic eruptions contain some water vapor, and that it may have been enough to account for the Earth's surface water. This still remains an open question, but whatever the case with water, there often comes life. Life most likely began during the late Hadean or early Archean eon, which lasted from 4 to 2.5 billion years ago. There's evidence of life in at least 3.8 billion-year-old rocks from Aquila Island, Greenland, and the oldest form of life discovered by scientists, tiny hematite tubes, estimated to be 4.28 billion years old. Hypotheses include a chemical origin of life in the early atmosphere, hydrothermal vents, deep-sea oceans, and even comets that came here from somewhere in space. It's highly possible that life began from the chemical environment of the early atmosphere and oceans, but they were nothing like we have today. The atmosphere was oxygen-free but abundant in methane, carbon dioxide, sulfur, and nitrogen compounds. Some space objects in our solar system are known to have an atmosphere like this. In one experiment, scientists simulated our planet's early atmosphere and lightning in a sealed vessel. They found that after igniting sparks, amino acids, the fundamental building blocks of proteins, were formed. Life that could have started on the deep ocean floor may have also been able to survive without photosynthesis due to another biological process called chemosynthesis. Instead of using energy from the sun, primitive life gained energy from the heat coming from the Earth's interior. Still, there's always a possibility that life initially originated in space and was then carried here by comets or other celestial bodies. Researchers have already found amino acids within meteorites and comets. What's exciting about this idea is that it means a high likelihood of life exists somewhere in space. The Earth has changed so many times and transformed heavily from when it first formed. How life came from non-life is still a big scientific mystery. However, we do have a current best guess for the beginning of life on Earth, which we think is around 3.8 billion years ago. But before we get into that, let's start from the beginning and take a trip back in time. One of those was giant insects called Meganeuropus, which closely resembled modern-day dragonflies and had wingspans of 63 to 68 centimeters and could be seen in the skies during this period. One incredibly detailed fossil of a huge dragonfly that died 320 million years ago was discovered to have a wingspan of 0.75 meters. Deadly poisonous centipedes 2 meters long crawled around with mammoth cockroaches and scorpions as big as 1 meter long. Amphibians began to diversify, and reptiles evolved into forms much like modern-day lizards, with a backbone allowing them to live and move on land. These amphibians were also huge, and some species were predatory, resembling modern-day crocodiles armed with sharp teeth and reaching lengths of almost 6 meters long. Like modern-day crocodiles and alligators, some evolved to have thicker, scaly skin, which solved the problem of their bodies drying out if they were out of the water too long. For the first time, amphibians evolved to lay amniotic or air-breathing eggs on land, and that changed everything. Since these animals could now live out of and away from water sources, the Carboniferous period gave way to the Permian period, which began approximately 300 million years ago, just 50 million years before the dinosaurs. All the continents during this period existed as one large landmass called Pangaea. The first large plant-eating and meat-eating animals evolved during this time. Some of these creatures could be mistaken for dinosaurs, but they were actually more closely related to mammals and reptiles. One of these bizarre creatures was Diplocerapsis. It looked a little like a salamander that averaged around 1 meter long, but its head was shaped like a boomerang. Another new reptile on the planet was the iconic Dimetrodon, which grew to about 5 meters long and had a large sail on its back, which is likely used to regulate its body temperature. During the Permian period, mammals were increasing in dominance. The biggest of these were creatures classified as Gorgonopsians, which were a class of giant bear-like animals that all had different teeth specialized for different functions. These animals could be either herbivores or carnivores and varied in size from less than a kilogram to more than a ton. One group of these creatures was known as cyanodonts. Their name means dog-like teeth, and these animals had social behavior, and there is some fossil evidence that shows they hunted in packs. In the oceans, fish with true bony skeletons evolved. Sharks and rays flourished, as well as sponges and coral. On land, insects evolved with adapted mouthparts that allowed them to pierce and suck. Around 252 million years ago, the Permian era came to an abrupt end by a cataclysmic event that caused mass extinction. In 2001, scientists made a chilling discovery: a massive comet or asteroid, similar to the one that put an end to the dinosaurs, wiped out the giant reptile predecessors 200 million years earlier. But how did scientists come to this conclusion? Molecules of helium and argon gas were found locked in carbon in high proportions that could have only come from space. It's estimated that the asteroid or comet was between 6 and 12 kilometers wide in diameter. Researchers say the strike would have released the energy 1 million times greater than the biggest earthquake of the last century. Aside from this discovery, there's some evidence that present-day Siberia and China experienced volcanic eruptions on an unimaginably massive scale, and those eruptions created dust and ash clouds that blocked out sunlight. Not only that, but over 1 million years, 3 million cubic kilometers of lava poured out of the ground, covering the entire planet in a layer 10 meters thick. The asteroid impact, combined with volcanic activity, was the proverbial blast from a double-barreled shotgun. The Earth was once again a very unhappy place. The combination of these two events resulted in what's called the Great Dying. 90% of all marine animals and 70% of all land animals that were alive during this time perished. 252 million years ago, ancient life on Earth suffered a serious blow from a deadly combination of heat and low oxygen. 95% of all marine species perished, and 2/3 of terrestrial species vanished. It was a cataclysm so severe that it looked like the end of all life on planet Earth. But, as the saying goes, life finds a way, and the most well-known prehistoric creatures would rise on Earth: the dinosaurs. If you love dinosaurs, then get ready to see your favorites, how they evolved, and how they would rule the Earth for millions of years. The extinction event of the Permian-Triassic era, 252 million years ago, marked the beginning of the Mesozoic era, which included the Triassic, Jurassic and Cretaceous periods, lasting 186 million years. During the Triassic era, there was one vast supercontinent called Pangaea, which was mostly vast deserts with a hot and dry climate, surrounded by a huge ocean called Panthalassa.
Dinosaurs would begin to evolve during the mid to late Triassic period. When we talk about dinosaurs, we immediately imagine towering and thundering animals like Tyrannosaurus rex. But new research shows that the dinosaurs and their pterosaur relatives evolved from extremely small ancestors. Proof of this theory was discovered in Madagascar when a newly discovered reptile species was found and named Kongonophon kelly, or tiny bug slayer. It lived some 237 million years ago and stood just 10 centimeters tall. It is one of the first small animals found from the root of the Ornithodora family tree and is an important discovery. The miniaturization event in which it lived served as a survival strategy for early Ornithodora, and wear on its teeth showed the tiny creature preyed on insects. This eliminated the need for them to compete with their relatives for meat. Furthermore, researchers of this tiny dinosaur relative showed that feathers and other fuzzy skin coverings found on the later true dinosaurs and pterosaurs likely originated to protect the tiny dino ancestors from the extreme climate of the mid to late Triassic period. When the first dinosaurs evolved, the Triassic marked the rise of the reptiles, mainly the archosaurs or ruling lizards and the therapsids or mammal-like reptiles. For reasons unknown, the archosaurs had an evolutionary edge, muscling out their mammal-like cousins and evolving by the mid to late Triassic into the first true dinosaurs, such as Eoraptor and Herrerasaurus. Dinosaurs were divided into two main branches: Saurischia, which means lizard-hipped, and Ornithischian, or bird-hipped dinosaurs. Eoraptor was at the root of the Saurischia family tree. It was only 91 centimeters long and weighed about 11 kilograms. It had long legs that allowed it to run fast, and its front paws had sharp claws that helped it to grab prey. Herrerasaurus was more advanced in evolution than Eoraptor because it had a joint in its lower jaw. It had a large skull, and its jaws were armed with the sharp teeth of a carnivore. It averaged in length from 3 to 6 meters and had 5 fingers on each paw with blunt claws. Styracosaurus was another early true dinosaur that was about 2 meters long, with a large skull as long as its femur. There were 13 to 14 sharp teeth in its upper and lower jaws. It had short front paws with 5 fingers and long hind legs that allowed it to run fast. Styracosaurus was a predator that weighed about 30 kilograms, and although this dinosaur was kind of small, it probably had no trouble dealing with larger prey. Eoraptor, Herrerasaurus, and Styracosaurus are prime examples of the rapid evolution of predatory dinosaurs 225 million years ago. At the same time, the first plant-eating dinosaurs appeared in the fossil record. Pisanosaurus was a 1-meter dinosaur that weighed 2 to 9 kilograms and had closely spaced teeth, forming a continuous edge for grinding plant matter. By the late Triassic period, there were at least 15 different dinosaurs. During the Jurassic period, Earth's climate changed from hot and dry to a much more humid and subtropical climate. Forests of ferns, cycads and conifers began to cover the planet, and the air was warm and moist with tropical breezes. During the beginning of this period, the breakup of the supercontinent Pangaea continued and accelerated. Laurasia, the northern half of the continent, broke up into North America and Eurasia. The southern half, called Gondwana, began to break up during the mid-Jurassic. The eastern parts, Antarctica, Madagascar, India and Australia, split off from the western half of Africa and South America. New oceans flooded the spaces in between. Huge mountains rose on the seafloor and pushed sea levels higher onto the continents. It was all this water that created the humid and subtropical climate. Deserts began to turn green. Palm tree-like cycads and conifer trees such as the araucaria and pine were abundant. The oceans became full of diverse and abundant life, and at the top of the ocean food chain were the marine reptiles, the plesiosaurs with their long necks and paddle-finned flippers. Among them were giant marine crocodiles, sharks and rays. Ichthyosaurs, squid-like cephalopods, coil-shelled ammonites, sponges, snails and mollusks were abundant in the ancient ocean. Coral reefs grew and expanded quickly in the warm waters, and microscopic plankton increased rapidly to the point that they may have turned parts of the ocean red. The earliest known bird, Archaeopteryx, took to the skies in the late Jurassic. It likely evolved from an early Saurischian dinosaur. Archaeopteryx had to compete for airspace with pterosaurs, flying reptiles that had been buzzing the sky since the late Triassic. Meanwhile, insects such as leafhoppers and beetles were abundant, as many of Earth's earliest mammals scurried around the feet of dinosaurs. It was at this time that the dinosaurs began making their mark in a huge way. Literally, small quadrupedal plant-eating dinosaurs gradually evolved into multi-ton giants. The plant-eating sauropod named Brachiosaurus was 16 meters tall and stretched out to around 26 meters long, weighing as much as 25 tons. Another herbivorous sauropod giant named Diplodocus was 27 meters long and weighed between 30 to 50 tons. The sheer size of these dinosaur giants may have stopped the attacks of a bulky meat-eating dinosaur that walked on two powerful legs and also lived during this time, the ominous Allosaurus. This huge carnivore ranged in size from 7 to 12 meters long, weighed nearly 2 tons, and had 16 sharp teeth in its upper and lower jaws. Like many predatory dinosaurs of the Mesozoic era, Allosaurus constantly grew, shed, and replaced its 3 to 4 inch teeth. This dinosaur was fast. Models suggest that Allosaurus could run up to 34 kilometers per hour. Fossil evidence shows that Allosaurus preyed on Stegosaurus, and the plant-eating dinosaur fought back, punching holes right through Allosaurus's bones with its spiky club tail. It could be why Stegosaurus had a pretty long run and survived all the way up to the late Cretaceous.
But there were new predators that would come along that were equally terrifying as Allosaurus. The North American Tyrannosaurus rex could grow 12.5 meters long and weigh up to 8 to 10 tons. Although now some say it might have weighed half of these estimates, the T-Rex wasn't alone in the meat-eating dinosaur category. In fact, it was either outclassed or equal to two other sharp-toothed monsters. The South American Giganotosaurus, which had the same type of build and weighed 9 tons, and the 10-ton Northern African Spinosaurus. Still, the T-Rex was a mean and nasty predator, if not downright unhygienic. Experts believe that shards of rotten, bacteria-laden meat were constantly lodged in its closely packed teeth, which gave the animal a septic bite that would eventually be fatal to its wounded prey. Of course, this process would have taken at least several days or weeks, and another T-Rex would probably reap the rewards. Scientists examining the T-Rex skull determined it had the bite force of between 1,500 to 5,000 pounds per square inch and could take bites of flesh in the 225 kilogram range. But Tyrannosaurus rex, like Allosaurus, had problems with prey itself. It lived in the same region and time period as some armored plant-eating dinosaurs. One of the most iconic dinosaurs next to T-Rex has to be Triceratops, which means three-horned face. All Triceratops had three-horned skulls. 2 massive horns were above the eye sockets, and 1 smaller horn was over the nose. Weighing around 6.5 to 13 tons, the biggest Triceratops was 9 meters long from nose to tail. The tips of their shoulders were 3 meters off the ground. Triceratops had teeth arranged in dental batteries, and each individual tooth was stacked in a vertical column of 3 to 5 teeth. These formed rows with 36 to 40 tooth-loaded columns. This means that a single Triceratops could have 800 teeth at its disposal. It had a narrow beak and powerful jaws that allowed it to grind down tough vegetation and trees. It was one of the last non-avian dinosaurs to evolve at the end of the Cretaceous. Ankylosaurus is another of the most famous armored dinosaurs. It was the largest ankylosaurid and the last of its kind. It's thought to have lived right up to the end of the Cretaceous period. The body of Ankylosaurus was covered in bony plates. It had a beak and teeth, and 4 horns that projected backward from its head. Its tail ended in a club, which provided protection from predators. This would have been useful since Ankylosaurus lived alongside Tyrannosaurus rex and other meat-eating predators. At some point during the middle of the Cretaceous period, Dinosaurs from the ornithopod family evolved into the popular hadrosaur, or duck-billed dinosaurs. They were large, oddly shaped, low-slung vegetation eaters with tough beaks on their snouts, which were used for shredding vegetation. These dinosaurs are believed to have lived in herds and were capable of walking on two legs. Sauropods became even bigger by the late Cretaceous period. You may have thought that Brachiosaurus and Diplodocus were big, but by the time the late Cretaceous period rolled around, there was another dinosaur that existed which could possibly be the biggest land animal that's ever walked the Earth, Argentinosaurus. This behemoth could be 30 to 40 meters in length and weighed between 50 and 100 tons. It was a member of the Titanosauria, the dominant group during the Cretaceous period, and was a herbivore like its earlier sauropod cousins. There was also a strange new breed of dinosaur that lived 20 million years before they all went extinct. They were called Pachycephalosaurus, or bone-headed dinosaurs, and had a bizarre-looking skull with horns on the snout and around the base of the skull. These could have been used to fight off the last of the big predators or even to show dominance over their own species. Of course, there are more than 700 different dinosaurs that have been found so far, but not enough time to cover them all in one video. There are some dinosaurs that lived in the colder regions when they were further south and within the Antarctic Circle during the Cretaceous. During this time there could have been some snow and ice and temperatures as low as -10 degrees Celsius during the 3-month-long dark winters. There were a variety of different dinosaurs living in this polar zone. In 2014, a skull section and upper and lower jaw bones were found of a miniature T-Rex called Nanyxsaurus hoglandi. It's believed that many dinosaurs had feathers to protect them from the elements, and this tiny T-Rex cousin was about 6 meters long. It's now believed that all species of Tyrannosaurus rex had feathers to protect them from the elements, and Nanyxsaurus was no different. Other dinosaurs, like the horned dinosaurs and duck-billed dinosaurs, along with other small feathery predators. Other dinosaurs, like the horned and duck-billed dinosaurs, along with other small feathery predators, parrot-like oviraptors, and a small herbivore named Leilanisaura, lived in the polar region as well. But their time would soon come to an end. Everyone talks about how dramatically the dinosaurs went extinct, but judging by the whopping 165 million years they survived, they might just be the most successful vertebrate animals to ever exist on planet Earth. In fact, some dinosaur relatives are still around on the planet today. Modern-day birds are in fact descendants of feathered dinosaurs. You might be surprised to learn that crocodiles are the closest living relatives to birds, as they shared a common ancestor. Everyone knows that a giant rock from outer space hit the planet millions of years ago and wiped out the dinosaurs. Now, with advanced technology, researchers have been able to put together a new timeline showing what really happened. Not only this, but they think they know where the giant asteroid came from. Is Earth the target for another huge space rock, and would we be able to survive? You'll be surprised and probably shocked at what NASA astronomers recently discovered. So now, get ready to experience the disaster that almost wiped out life completely on Earth. The giant asteroid's impact into shallow waters in the Gulf of Mexico 65 million years ago was bad enough, but then an amalgam of additional disasters ensued. Rocks fell from the sky, wildfires ignited, and tsunamis inundated distant shorelines. The researchers found that the first day of the Cenozoic was peppered with cataclysms and released a new record of this day of chaos in proceedings of the National Academy of Sciences. Their timeline was developed using high-resolution photography, microscopy, computed tomography imaging, and magnetic measurements of hundreds of feet of sedimentary rock recently recovered from Chicxulub, one of the largest impact craters on Earth. And it all began like this. Imagine you were somewhere in North America about 65 million years ago when dinosaurs ruled the Earth and you were looking up at the night sky. You would have probably seen what appeared to be a bright star shining off into the distance. But if you watched this peculiar light for an hour or two, the object would seem to grow in brightness but barely move. Hours later, the asteroid plows through Earth's atmosphere, heading straight for where the Yucatan Peninsula is today. At impacts of that speed, Earth's atmosphere acts like water. Smaller space rocks, called meteors, hit the atmosphere like pebbles thrown into a pond and decelerate rapidly at high altitudes, burning away from the friction of the atmosphere. While some bigger pieces of rock survive and fall to Earth, the mountain-sized Chicxulub asteroid hits our atmosphere like throwing a boulder into a puddle. The asteroid shrieks over Central America, emitting the mother of all sonic booms that would shatter eardrums across all the continents. The dinosaurs were likely terrified and running in all directions, having no idea what was just about to happen. But if any animal was close enough to see the asteroid, they would have been instantly vaporized within minutes. In fact, except for sea turtles and crocodiles, no four-legged animal larger than 25 kilograms would survive. The mountain-sized space rock falls so quickly that the air itself cannot escape. Under intense compression, the air heats to thousands of degrees almost instantly. Before the asteroid even hits, compressed superheated air vaporizes much of the shallow sea that covers the Yucatan. Milliseconds later, the rock plunges through what's left and slams into bedrock. In that moment, a chain reaction of events occurs. The impacting asteroid exerts so much pressure on the Earth that soil and rock flow like fluids. The flowing up and down movement of the Earth is like the double splash of someone doing a cannonball in a swimming pool. The initial splash in all directions is followed by a delayed vertical splash when the cavity created by the asteroid rebounds to the surface. The first wall of Earth gouged outward at the moment of impact is more than 32 kilometers high. When the cavity rebounds to form the delayed vertical splash, the Earth rises at over 1,600 kilometers per hour to heights taller than Mount Everest. Within minutes, this mountain of debris almost entirely collapses in a series of secondary explosions, leaving behind a smaller mound called a crater's peak ring. At the same moment the asteroid strikes the Yucatan and applies its pressure to the bedrock, it converts the kinetic energy of a 7.5 billion-ton rock traveling 16 kilometers per second into searing heat. In an instant, the Chicxulub impactor delivers approximately 1 septillion, 300 sextillion kilojoules of energy, more energy than 1 billion Hiroshima atomic bombs. The kinetic energy transferred by the asteroid to the soil, rock and air excites the molecules to temperatures far hotter than the surface of the Sun. The heat rips electrons from atoms, ionizing the air into an expanding fireball of plasma in excess of 10,000 degrees, turbocharged with vaporized rock that's blasted out at hypersonic speeds. The heated, rapidly expanding air and near-instantaneous conversion of Earth to gas, combined with the impact shockwave itself, form a massive blast wave of pressure expanding outward at more than 1,600 kilometers per hour. If this asteroid hit the same spot today, the blast wave would vaporize you in Texas, deafen you in New York, and blow out glass windows in Buenos Aires. The Chicxulub impactor rings Earth like a bell. Waves in Earth's crust radiate away from the impact zone at 4 kilometers per second. The waves then trigger fault slipping and earthquakes across the continents. If you're on the other side of the world, you would feel the ground shaking 30 minutes after impact. The impact triggers tsunamis as high as skyscrapers. The first of them hit Gulf coastlines within the hour. Waves ranging from 600 feet to perhaps as tall as 1,000 feet smash into what is now Mexico and the southern United States, flooding tens of miles inland. The waves temporarily reverse the flow of rivers, rushing up riverbeds like 30-foot tidal bores. Tsunamis smash into the eastern coast of the United States, and 6 hours after impact, they max out at 600-foot high walls of water that slam into Europe, Africa, and the Mediterranean coasts. Within 15 hours of impact, waves arrive on every coastline on the planet. Depending on local topography, the ocean sweeps away anything in its path and sucks it back to the sea when the waters finally retreat. It already sounds like Armageddon, but even more disasters are on their way. When the big rock strikes, its splash accounts for 25 trillion tons of earth that it launches on ballistic trajectories, some at speeds that exceed Earth's escape velocity. These rocks excite Earth's gravitational pull to either orbit the Sun, and some of this material probably reaches the Moon. However, the majority of ejected debris returns back to Earth within the hour. These glass-like chunks, called tektites, some as large as buses but most the size of marbles, pelt the Earth at speeds ranging from 160 to 320 kilometers per hour in lethal quantities. Regardless of where any remaining dinosaurs were on Earth, they were hit with this fiery hailstorm. But these glass bullets didn't need to hit the dinosaurs to be fatal. As these tektites fall, their friction with the atmosphere emits enough thermal radiation to set fires across the planet. By some estimates, the combined heat of the returning embers heats the planet to the equivalent of an oven set to broil. Most of the world's trees burn, which is perhaps why the only bird species that survive the impact are those that nest on the ground. Of the few larger land animals to avoid extinction, nearly all had some means of escaping the heat. They could either burrow, like small mammals, snakes and lizards, or escape into water, like crocodiles or turtles. Even if the poor dinosaurs were on the other side of the world, they would have needed to find protection from the initial heat blast. In a final piece of terrible luck for the dinosaurs, Chicxulub happens to strike an area rich in oil and sulfur. The impact ejects 100 billion tons of vaporized sulfur and 30,000 quadrillion gallons of water into the atmosphere, which then condenses into massive storm clouds and falls back as torrents of acid rain that acidified the oceans. In the higher latitudes, continent-wide snowstorms deposit tens of feet of snow per day. But the global deluge doesn't last long. In addition to water, Chicxulub vaporizes and explosively ejects 150 football stadiums worth of oil from the Yucatan bedrock. This oil condenses in the stratosphere as a black layer covering the Earth like a coat of black paint. Unlike the sulfur and wildfire smoke, the carbon circulates high above the cloud layer, stopping it from raining back down. That becomes another big problem. The soot layer remains in the atmosphere, reducing the amount of sunlight that reaches Earth's surface by 90% for at least 2 to 3 years. The initial oven-like heat brought on by the returning tektites is followed by a deep and long-lasting freeze. Global temperatures drop by an average of almost 50 degrees. The only places on Earth to avoid this deep freeze are Madagascar, India, and Indonesia, which were tropical islands during this time. In the global chill, evaporation almost ceases, dropping rainfall by 80%. Nearly every spot on Earth outside of these tropical islands dries into a desert. Where did this giant rock come from? And is there another one out there headed for us? Researchers, using a supercomputer, studied asteroid evolution using data from known asteroids. The two-member team of Avi Loeb and Amir Siraj suggested that the Chicxulub asteroid likely originated from the Oort cloud. a sphere of debris at the edge of the solar system. It could have been a much larger comet pushed off course by Jupiter's gravitational field and sent close to the Sun, where it broke into several pieces. These fragments can cross Earth's orbit and hit the planet once every 250 to 730 million years. Judging from this study, it's not a matter of we could be hit by another giant rock from outer space, but on Saturday, December 11th, 2021, NASA revealed that a 330-meter-long asteroid named 4660 Nereus screamed past Earth around 3.8 million kilometers away at a speed of 6.5 kilometers per second. While you might not think this is very close, any slight deviation in its orbit could put it on a direct course with us and smash into the Earth in the future. Astronomers are tracking this potentially hazardous rock and say it'll come within 1.1 million kilometers of Earth on Valentine's Day in 2060. Buy your flowers and get those proposals done early, just in case. Keep in mind, the asteroid that caused the Chelyabinsk explosion in Russia in 2013 was just 20 meters in size. The bad thing is that we don't have any known way to defend the Earth from a giant space rock. However, NASA's DART mission, or Double Asteroid Redirection Test, will try to see if a spacecraft can autonomously navigate to a target asteroid and intentionally collide with it, causing a kinetic impact that could push the asteroid off a collision course with the Earth. DART's target is Dimorphos, an asteroid moonlet that orbits a larger asteroid named Didymos. The spacecraft is set to arrive in late September 2022, when the Didymos system is 11 million kilometers from Earth. However, it's estimated that the collision will change the speed of the moonlet by a fraction of 1%. Stopping a 10-kilometer wide or larger asteroid hurtling towards the planet at more than 72,000 kilometers per hour will take a lot more than a small spacecraft impacting it. Perhaps the world would need to try nuclear weapons, like in the movie. Maybe you have an idea of how we could stop a world-ending asteroid and become famous. Let us know what you think, and make sure to stay tuned here for more exciting stuff happening in our universe. Thanks for watching.